Continuing from yesterday, our lecture on action potential, we've got our framework for the most part, background laid down. So let's start right here. Okay. The resting, yes, the resting neural cell membrane is set and ready for action potential in much the same way that dominoes are set to fall. What makes all the dominoes fall down? The first one. Yep, just have to tap the first one and then the rest of them fall down. Okay? Now, what is it that's set up in our neurons? What's continually being reset back into place? Sodium and potassium ions are being put back. So here we go. So the dominoes in neurons are ions being placed on the correct side of the cell membrane by sodium potassium pumps. All right. We're going to draw a little section of membrane here. More phospholipids. And I had him draw 2 of these earlier today, and I think I just want to stick with 1. I don't want to confuse you. Oh, certainly. Uh-huh. This is just one little section of membrane. Yeah, those are sodium ion channels. And then we're going to do a potassium one. All right. I'll go ahead and throw one of these in here so we can get the party started here, right? Okay. Okay, we got our little pieces here. Start dividing them out. And what I've got here is just little dots that are punched out of the hole punch, and the blue ones were to represent what? What was it again, gang? Sodium atoms or ions? Ions. They're ions because they have a charge, okay? Now, these things right here, the sodium-potassium pump is going to work to reset this business. Okay, it's going to pump these things. It's going to pump sodium out of the cell while pumping potassium into the cell. So this is going to send those out and these in to get everything set up right. So go ahead and push yours through here. And make sure you're using the sodium-potassium pump. None of the other things that are in the membrane can actually do that. This one's a little half of an ion. Got a little excited with that. And it exchanges some for some. If you can do that, that'd be great. If not, don't sweat it. And it's taking energy to do that too. Energy in the form of what? ATP. If we need to save just a few of these back, that's okay. Okay, tuck a few of these sodiums over to the side here. They're going to come into play in a little bit. Now, spread these guys out. Why? They would naturally do this. What force would spread them out? Diffusion would. Diffusion would keep these all spread out somewhat evenly. Okay, so you're going to have a relatively even distribution of sodium on one side and a relatively even distribution of potassium on the other side. Okay, and to be clear, this is inside cell, this is outside cell. Okay. Alright, so action potential steps. Number one, membrane is depolarized to minus 55 millivolts, which is the threshold value. Basically, if this number is going to is getting smaller or moving towards zero or past zero, that's called depolarizing. It's called depolarizing. Now, what happens here is something really, really important, okay? This change in transmembrane potential causes voltage regulated sodium channels to open. The sodium channel, all these things are closed here, okay? But something causes it to open, and what causes it to open is this change in voltage. That's why this voltage matters, because there's proteins in here that open and close and change their shape in response to changes in voltage. Okay? Now, the reason we kept these little sodium ions here is because these are the dominoes that are going to set everything off. Okay? They're coming from upstream for reasons that I'll explain a little bit later on, but they're floating this way. All of a sudden now, these sodium ions being in here changes this transmembrane potential. Instead of being minus 70, it's minus 55. It causes this voltage regulated sodium channel to open. Then what happens? If this opens, what now? Yes, it does. Sodium then is allowed to pass through into the cell. And just sodium, and only in. The reason it comes in is because there's a greater concentration of it on the outside than there is the inside. So sodium then floods into the cell. Okay? What do you think that does to this number here? It's going to decrease it. So much so that it takes it the opposite direction. It goes all the way to plus 30. It has flipped the polarization from the inside to the outside, which is why it's called depolarization. But I need to explain one important principle here first, and fortunately for us, it's got a really simple, straightforward name. It's called the all or none principle. What it simply states is this: if depolarization goes to the threshold value, then an action potential will take place. If not, no action potential takes place. That's the basic idea behind it. I'm going to throw a trigger analogy here for you. If you've ever fired a gun before, you can apply a certain amount of pressure to the trigger and nothing happens, and a little more even, and nothing happens. But once you apply exactly enough pressure, that trigger breaks over and the gun fires. There is no partially fired a gun, or I fired the gun halfway, or the bullet went half as far because I didn't squeeze it as hard. It's all or nothing. Either it happens or it doesn't. That's how your neurons work too. If you reach this threshold value, your neurons fire. If you don't, then they just don't. Okay. Alright, so the sodium is flooded into the cell, so let's mention that. Sodium ions, we're going to say diffuse into the cell. Changing the transmembrane potential to plus 30. So we go all the way from minus 55 to plus 30. So all the way even into the positive range, which means that now we have more positive charges on the inside of the cell than we have on the outside of the cell, which is why it's depolarized. Okay. Now this is important. At plus 30, voltage regulated what? It's going to open. Only one thing left we didn't mention up there. Yes. Yes, voltage regulated potassium channels. Open. allowing potassium ions to diffuse out. Okay, so let's move those guys out. So now we're at plus 30. These dudes are going to diffuse out. Okay. And that's going to happen until we reach about, this little half guy, we'll put him out there too. That's going to reach out until we reach about minus 80. There is a brief refractory period called hyperpolarization. And let's mention that down here, number 5. Running out of room down here. Potassium diffuses out. Till the membrane is repolarized and hyperpolarized to minus 80 millivolts. And then after that, return to normal resting potential. Let's try this. Okay. I want you to put, oh boy, watch your letter P. If you're gonna fly these things out of there. We're gonna do the y-axis of a graph right here. Minus 70, minus 55, 0, plus 30, minus 80. Okay. All right, let's use our sodium-potassium pump to get us back to normal. Even though we were normal with like numbers here, we weren't normal because we're missing some stuff that's supposed to be on the inside and supposed to be on the outside. We got to exchange these. So let your pump work, folks. Go ahead and let your pump one out for one in. Though it's not exactly like that. It'll work. I think it's like 2 for 3 it exchanges, but there is an exchange. Sodium out, potassium in, sodium out, potassium in. Okay, so let's get the stage set one more time. And I'm going to take my weird guy right here and I'm going to put it on the graph. Okay? If we're at rest right now, what should the resting membrane potential be? If we're at complete and total rest. This is from yesterday. Minus 70. Okay. So we're going to hang out here at the beginning. Okay? Then what happens, not from there, but what happens is a couple of sodium ions, actually a bunch of sodium ions, flood in from downstream. Okay? What does that do to the membrane potential now? To what? Not quite yet. What is it right now? Minus 55. This small change allowed this to go to minus 55. But at minus 55, this channel is going to open up. And when this channel opens up, what's going to happen? They're going to diffuse from high to low concentration. These sodium ions are going to flood in. And now what happens to this number? It goes all the way to plus 30. Okay? All right? And at plus 30, what happens? Potassium channels, they open up and allow for potassium to flood out, making the outside positive once again. And that causes this to go from here and just briefly past there to minus 80 before these channels close up, and then it levels back out again right there. So if you follow the graph, what happens is this. Over time, it goes from here to here, all the way up to there, back down like this, and back up. If this is time down here. And this happens really fast. So this little dude representing the transmembrane potential is going to go from rest to threshold, from threshold to plus 30, briefly down to minus 80, and then level back out again at minus 70. So that's the gist of it. But this is only one little section. What happens is a chain reaction. You see, I showed you that a couple of sodium ions came in from downstream here. That's where these guys are going. As they diffuse out, they're going to diffuse over to the next section of these little deals right here, and are going to depolarize the next section. So in a neuron, if you can imagine it, we have all these little sections like this. It's not going to be the best here, but I'll give it a run. Whoa, like I'm using chopsticks. All the way down, we're going to diffuse, the sodium ions are going to diffuse. So one little section at a time will be depolarized right here, while the rest of it is still polarized. And this is going to change. So from here to here, this will be positive, and that'll be back to negative. And this will be positive, and this will be back to negative. And that'll be positive, and this will be back to negative. So it's like a chain reaction, which is why I use dominoes as the analogy. One starts, and it starts a chain reaction that happens all the way down the neuron. Okay. That's quite a bit of information for today, so let's I want you to practice that through a couple times and kind of let that sink in.